Okay, imagine a problem set, right? So simple. A 5-year-old can probably knock it out in like 10 minutes. We're talking tasks that humans find trivial, like 100% accuracy when tested. Now picture this. That same set of problems. It's been a 5-year nightmare for basically every advanced AI out there, including the huge models we hear about constantly.
That's exactly it. We're talking about the abstraction and reasoning corpus. ARC-AGI, it's kind of become the benchmark for measuring what some people call true generalization.
Right, generalization, not just recognizing patterns it's seen before, but actually figuring out something new.
Precisely. It's about the ability to efficiently pick up a new skill, solve a problem you weren't specifically trained on. It's aiming for, the essence of intelligence, not just showing off a pre-learned skill.
And today, we are diving deep. We've got the technical report from the ARC Prize 2024 competition, because after years of basically hitting a wall,
Yeah, stagnation is a good word for it.
suddenly performance jumped, like really jumped. So we're going to unpack how that happened, what new techniques broke the logjam, and how this might be changing the whole AGI roadmap.
Yeah, our mission here is really to get under the hood of those algorithmic shifts, what finally moved the needle. And, how close did anyone actually get to that $600,000 grand prize? They set the bar at 85% accuracy. We want to know why just throwing more compute at it failed for so long, but these newer, maybe cleverer algorithms started succeeding.
Okay, let's paint the picture of the task itself, because for you listening, it sounds almost ridiculously simple. You get these grids, right? Input grids, output grids. Usually about 3 examples showing a transformation-colored cells moving or changing.
Just a few demonstration pairs.
And your job, or the AI's job, is to figure out the hidden logic, the rule, and then apply it to one final test input grid to produce the correct output.
And the kicker is the only prior knowledge allowed is what they call core knowledge, basically stuff humans get by age 4.
Like what? Objectness. Things are things.
Yeah, objectness, basic shapes, and how they relate spatially, like topology and, simple counting and arithmetic. That's it. No pre-training on ARC tasks themselves, ideally.
Which brings us to the paradox. You said humans aced this. Original testers, 97, 98% individually.
And together, collaboratively, they solved 100% of the private tasks used in evaluations. It's easy for us.
But for AI, historically a disaster zone.
Total graveyard, yeah.
Yeah.
And to really appreciate this recent jump, you have to understand why traditional AI, especially deep learning, just crashed and burned here for so long.
It's good at learning from data, right? So what's the problem?
It's good at relating new situations to known situations it saw in training. Think image recognition. It's seen millions of cats, so it recognizes a new cat picture.
Okay, makes sense. Interpolation.
Exactly. But ARC tasks often require extrapolation.
Oh.
Each task has a novel logic, a unique little program you have to figure out and apply. The classic deep learning setup. It offers zero adaptation at test time. It uses what it learned, but it doesn't learn how to learn for this specific new task in front of it.
So it couldn't generalize the process of solving these kinds of puzzles.
Pretty much. And the failure stats are, well, stark. That 2020 Kaggle competition. The deep learning methods. They scored less than 1%.
Less than 1%. And wait, get this. The original GPT-3, the model that amazed everyone, they tested it via direct prompting.
Zero. A clean 0% on the public evaluation set.
Wow. Okay. That's humbling for the big models.
It's stunning proof, really, that just scaling up parameters and training data, which was the dominant trend from 2020 to early 2024, wasn't cracking this nut. It increased skill on known stuff, but not this kind of generality.
So progress was glacial. You said the top scorer on the private set only went from 20% in 2020
to just 33% by early 2024. 4 years for a 13-point gain. The field was sort of stuck in that scaling paradigm.
Which sets the stage perfectly for the ARC Prize 2024, launched last June, right? The explicit goal was to break that cycle.
Yes, incentivize new thinking, demand open-source code sharing. And that big target, 85%.
And did it work?
Oh, it worked. Big time. In just 5 months, the state-of-the-art, the best score achieved, jumped from that 33% all the way to 55.5%.
Whoa, 55.5%. That's a huge leap.
It is. Minds AI got that top score, though they weren't eligible for the main prize because they didn't open source everything. But the top open source team, called the Architects, they hit 53.5%.
Okay, 53.5% is still massive progress. That's more than 20 points in half a year.
Exactly. Compared to 13 points in the 4 years before that, something fundamentally shifted.
Now, you mentioned something earlier about compute budgets. This is where it gets really interesting, especially for the scale is all you need narrative.
Yes, this is a key finding in the report. They ran two leaderboards side by side. There was the standard Kaggle board, strict rules, a tiny $10 compute budget per submission.
$10. Okay, that's forcing efficiency.
And they had the ARC-AGI pub board, much looser rules, internet access allowed, and critically, up to $10,000 in API credits for compute.
Wait, 10,000? That's 1,000 times more compute allowed on the second board.
1,000 times, yes.
Yeah. So surely the scores on the big budget board just blew the cheap one out of the water, right? If scale matters most.
That's what you'd expect. But no, that's the surprise. The top scores on both leaderboards tracked remarkably closely.
Seriously. The $10 K board wasn't significantly ahead of the $10 board.
Not significantly, no. Which strongly suggests, well, the report puts it clearly, algorithmic improvements towards AGI hold significant power, and that massive compute may not be necessary to crack ARC-AGI.
That's huge. It's saying the idea is the algorithms are potentially more important than just throwing trillions of parameters and megawatts at the problem.
It certainly points that way for this specific challenge. It's about algorithmic cleverness, about the approach to generalization.
Okay, so if it's about the algorithms, let's break down these new frontier approaches that push the score past 50%. You said the old way back in 2020 was mostly brute force program search.
Yeah, the 2020 winner got 20% basically trying out lots and lots of simple programs. But that hits a wall fast. Too many possibilities.
So what changed? What are the new camps?
Well, the progress seems to cluster around three main categories now, really centered on adapting to the task at test time. Two main competing philosophies, and then a third strategy that combines them.
Okay, approach one.
Approach one is deep learning guided program synthesis. This falls under the banner of induction.
Induction, like inducing the underlying rule or program.
Exactly. The system tries to figure out and literally write down the hidden program that transforms the input grid to the output grid. The deep learning guided part is the innovation.
How does deep learning help write programs?
Instead of just blindly trying every possible program, which is computationally impossible, that's the combinatorial explosion problem,
Right.
they now use specialized LLMs, particularly code-generating LLMs, to actually suggest plausible programs or to guide the search process towards more promising areas.
Ah, so the LLM acts like a smart assistant helping the search.
Kind of, yeah. Ryan Greenblatt's approach, for instance, used GPT-4o. It would generate thousands of Python programs for each ARC task, and then iteratively try to debug the ones that look like they might be on the right track.
Okay, that sounds smart. Using the LLM's intuition to prune the search space.
Yeah.
But does it work well? And what about the cost you hinted at?
It works better than pure brute force for some tasks, yes. But the cost is significant. The report estimates that to reach that 85% grand prize target using this method, you'd probably need to generate, evaluate, and debug something like 100 million programs per task.
100 million per task.
Yeah. Across the 100 private tasks, you're looking at a multi-million-dollar compute bill just for one run.
Oof. Okay, that's a major hurdle. And is it even clearly the best path right now?
Well, that's the other critical point. Right now, even with the LLM guidance, this induction approach doesn't seem to decisively beat the best pure brute force search methods when you compare them at similar compute levels. Both are hovering around the 40% solve mark on their own.
So, induction is smart, tries to find the true program, but it's incredibly expensive and maybe not scaling efficiently enough yet. That leads us to the competitor. Approach 2.
Approach 2. Test time training, or TTT. This is the main example of transduction.
Transduction. Different from induction how?
Transduction means you're trying to directly predict the output grid for the test input without necessarily writing down the explicit program or rule. You go straight from input examples to the output prediction.
Okay, how does test time training enable that?
This is the really clever bit, I think. You take a large pre-trained model, often an LLM, maybe one that's good with spatial reasoning, and for each new ARC task you encounter at test time, you quickly fine-tune that model just on a handful of demonstration pairs for that specific task.
Wait, you fine-tune the giant model on just like 3 examples?
Yeah, very fast, targeted fine-tuning. You're adapting the model's internal weights, nudging it to understand the specific logic of this one task before it makes the prediction for the test grid.
So it's like the model temporarily specializes itself for the puzzle it's currently looking at.
Yeah.
It's not static. It adapts on the fly.
Precisely. It becomes a rapidly adapting system. And the results show this is crucial for LLM-based approaches. Get this. The best score from a static LLM just doing inference No TTT, only 11%.
11%, compared to the TTT approaches pushing past 40%.
Exactly. TTT is basically mandatory if you want to use an LLM effectively for ARC right now.
Yep.
It dominates the transduction leaderboard.
Okay, I have to ask, though, if TTT relies on these huge pre-trained models, often trained on massive external datasets of ARC-like problems, things like RC-heavy or RSPU-Puri that people have created,
That's often part of the pipeline.
doesn't that kind of cheat, or at least undermine the spirit of true generalization from just core knowledge and a few examples if it's already seen thousands of similar logic puzzles?
That is the central philosophical debate right now. It's a really good question. Proponents of TTT argue it's still achieving the goal, efficiently acquiring a new skill from a few examples. The pre-training just gives it a vast library of building blocks or vector functions encoded in its weights. TTT is then just doing a shallow recombination of these existing, specialized blocks using gradient descent test time guided by the new examples. It's learning the concept quickly, like humans do, by leveraging prior, albeit vast, related knowledge.
Okay. That framing helps. So it's less about cheating and more about different mechanisms for adaptation. One searches for the recipe, the other tweaks an existing recipe.
That's a great analogy. Program synthesis, induction, is like writing a brand new detailed recipe from basic ingredients every time. It's deep, logically explicit, potentially very precise, but slow and costly.
Well, TTT transduction is like having a giant cookbook with millions of base recipes.
Right.
And when you see the 3 example dishes, you quickly find the closest recipe in the book and make a few notes in the margin, tweak it slightly to match the new ingredients. It's much faster, relies heavily on the cookbook, but maybe less guaranteed to be perfectly logical or explainable.
Exactly. Shallow recombination of vast, specialized knowledge versus deep recombination of small, generic primitives.
That makes a difference super clear. Okay, so we have induction, program search, and transduction, PTT. Why do we need approach 3, the ensemble strategy? Why not just pick the winner?
Because, it turns out, neither one is the whole story. The really crucial finding from the competition is that these two approaches, program search and direct prediction via TGT, solve significantly different subsets of the ARC tasks.
Oh, interesting. So they have different strengths and weaknesses.
Very different. A task requiring complex, explicit algorithmic steps might be easy for program search, but impossible for TTT. A task needing subtle visual pattern matching or rotation might be handled well by the adapted weights of TTT, but missed by the program search.
So to get the highest scores,
You have to combine them. All the top scores on both leaderboards, like the architects at 53.5% and Barbadillo, who also did well, use an ensemble. They run both types of solvers and combine the results. Remember, the best single approach, whether induction or transduction, seems to top out around 40% right now. Getting past 50% required the ensemble.
so the current state of the art isn't one breakthrough idea, but the realization that we need both adaptation strategies working together.
That seems to be the key lesson from 2024. And this success, this jump in score, is really making waves beyond academia.
Yeah, you mentioned industry impact. It's surprising how quickly a technical benchmark like this can pivot research labs.
The report explicitly calls this out. It notes several well-funded AI startups, they name Basis AI, Tufa Labs, AGMO companies with serious venture capital,
Millions in funding, yeah.
have apparently shifted their internal roadmaps significantly to prioritize cracking ARC-AGI. It's gone from a niche academic challenge to something seen as a real litmus test for next-generation AI capabilities by serious players. Corporate labs are spinning up efforts.
Because it measures something fundamental that scaling alone didn't capture.
Exactly. It differentiates systems on their ability to generalize and adapt, not just regurgitate.
But the benchmark itself, ARC-AGI version 1, isn't perfect, right? The report acknowledges flaws. Are we going to need an ARC-AGI 2.0?
Yes, definitely. The organizers and researchers are very aware of the limitations of the current private evaluation set. 2 main issues.
Okay.
First, size and exposure. It's only 100 tasks in the private set. That's quite small, statistically. And over 4 competitions now, the report says something like 10,000 scores on this private set have been reported back to teams via the Kaggle leaderboards.
10,000 probes on just 100 hidden tasks. That sounds like a huge risk of overfitting, even if indirectly. People might learn patterns of the test set itself.
Massive risk. Information leakage is a real concern. The integrity of the benchmark is potentially compromised over time.
And the second issue.
Task difficulty and type. An analysis revealed that a surprisingly large chunk of the original private set, 49%, was actually solvable by just combining various brute force program search methods, even back in 2020.
Wait, nearly half the test set could be beaten by brute force 4 years ago.
Yeah. It means almost half the benchmark might be overly susceptible to these simpler, maybe less intelligent techniques, and doesn't properly test the more advanced generalization capabilities we're hoping to measure.
So the benchmark needs a refresh to maintain its value.
Absolutely. And that's the plan. They intend to launch ARC-AGI 2 alongside the 2025 competition.
That will be different.
Key changes:
Hmm.
a much larger sample size of tasks for better statistical reliability. And crucially, they're planning two distinct evaluation datasets. One will be visible for providing intermediate scores during the competition, like the current private set, but the final ranking will be based on a second, completely sequestered, truly private dataset that is never scored until the very end.
Ah, that sounds much more robust. Prevents overfitting to the final measurement.
Exactly. It's about ensuring the benchmark continues to be a reliable driver of real progress.
Okay, so wrapping this up. This deep dive into the ARC Prize 2024 report really shows a field that was stuck, finding new momentum. The competition clearly worked, accelerating progress by focusing attention on adaptation at test time. That seems to be the
Deep learning guided program synthesis, trying to write the code, induction, or the test time training adapting the model itself, transduction. The ability to grapple with novelty during the test is what pushed the score from that stubborn 33% up to 55.5%.
It's a significant jump, a real proof of concept for these newer algorithmic ideas.
A huge psychological step forward, definitely.
Yeah.
But here's maybe the final thought to leave people with: that $600,000 prize for hitting 85%. Still unclaimed. The benchmark remains, well, unbeatable for now.
Right, 55.5% is great progress, but it's a long way from 85%.
And consider this: if 49% of the original set was solvable by brute force ensembles back in 2020, then maybe these sophisticated new methods, TTT and guided search, have only truly unlocked about 6.5 new percentage points of genuine, hard generalization capability over the last 4 years, from 49% to 55.5%. Seen that way, the remaining gap to 85% looks absolutely immense still. There are fundamental breakthroughs yet to be made.
That's a sobering but important perspective. The report authors argue, though, that the teams who will eventually build AGI, they're probably the ones thinking hard about ARC-AGI right now.
I think that's likely true. It forces you to confront the core issues of intelligence. So the lingering question for you, the listener, is: which of these paths seems more promising for closing that huge remaining gap? Is it the incredibly costly but perhaps more purely logical deep search of induction, finding that perfect recipe every time? Or is it the faster, knowledge-reliant adaptive fine-tuning of transduction via TTT, quickly tweaking the giant cookbook? That tension between cost, prior knowledge, logical depth, and adaptive flexibility, that seems to define the cutting edge of the AGI challenge today.